All right, so today we're going to go ahead and combine the idea of a Taylor and a Maclaurin polynomial with the idea of a power series for something that we call a Taylor series and a Maclaurin series. So we know that we can find a Taylor polynomial to approximate a function. And we've also seen that we can represent a function exactly with a power series, and at least over some interval, so not necessarily for all x values, but for some x values. And so if we put these two ideas together, we can find a Taylor polynomial, which will represent a function exactly over some interval, and we call that a Taylor series. And using the idea of a Taylor series, we can find a power series for any function that we want. Okay, so here's our definition of a Maclaurin series, which is just a Maclaurin polynomial that keeps on going. So it's that same formula that we've already seen, we just extend it past the nth term. And Taylor series, same sort of thing, just keeps on going. I want to find the Maclaurin series for y equals sine of x. Well, when we're finding a series, we don't have a real ending point, so we just need to find enough terms until we identify the pattern. So here's our formula. Let's go through and find the first few derivatives and see if we can identify what's going on here. So the value of the original function at 0 is 0. Take the first derivative, which would give us 1. Second derivative gives us 0. Third derivative gives us -1. And we know with sine and cosine, it's going to keep on repeating this pattern, 0, 1, 0, -1, and so on. So we can fill in the terms of the Maclaurin series. We can see that every time we have an even exponent, we're going to have a coefficient of 0. We start with x times 1, then we have x cubed times -1, positive, negative, positive, negative. So if we get rid of those 0 terms and simplify this down, we end up with this series right here. Now it's helpful to write this using sigma notation, so we need to identify how we can represent that. Well, we know that we're alternating positive and negative, so we have -1 to the power of n if we start with n equals 0. And we have odd exponents, we have odd factorials, and the way we can create an odd number using sigma notation is by using 2 times n plus 1. So if we start with n equals 0, 2 times 0 plus 1 is 1, and then go to n equals 1, 2 times 1 plus 1 is 3, then 5, and so on, giving us all of the odd numbers. So we have the series for sine of x. What we don't know yet is for which values of x this holds, because the interval of convergence isn't necessarily from -infinity to positive infinity. So let's go ahead and verify. All right, so we know we have this series for sine of x, and we can use the ratio test because this is a power series. So we take the limit as n goes to infinity, increase n by 1, and simplify. Cancel out any common terms, and we can see as n goes to infinity, we have x squared on top, which is a number, divided by infinity, which is 0. 0 is always less than 1, which means this series converges for all values of x. So we have the power series for sine of x, and we know that this converges for all values. All right, so if we want to find a Taylor series, differentiate with respect to x several times to find the pattern, and then plug that into the formula for the Taylor or the Maclaurin series. And then use the ratio test to make sure you determine the interval of convergence, because if we have a power series for a function, we need to know for which values of x we're allowed to use it. We need to know where that equality holds. All right, let's find the Maclaurin series for e to the x, and we want to determine the interval of convergence. So let's start by taking some derivatives of e to the x and evaluating at 0. And we know every derivative of e to the x is 1. Plug that into our formula. And writing this in sigma notation, we have the sum of x to the n over n factorial. Let's check the interval of convergence. So use ratio test, simplify it down, and this always goes to 0, which is always less than 1. Which means the interval of convergence is from -infinity to positive infinity. Now we can find the power series for any function using this technique. The complete list you need to know is in your quiz packet, so make sure you take a look at that, and through your homework you'll go through and construct quite a few of these.